Could Anomalocaris, the apex predator that ruled Earth's oceans 508 million years ago, survive the alien deep of Subnautica 2? On paper, that sounds like a fair fight. This animal sat at the very top of the Cambrian food web. It was the thing everything else was afraid of, the first large-bodied predator in the history of complex life. But one number deflates the whole idea. The largest well-preserved specimens of Anomalocaris canadensis measure around 38 to 50 centimeters long, under half a meter. That is a predator a person could hold in two hands. Older reconstructions sometimes padded it to a meter, even two. The best preserved fossils and more careful modern work bring it back down to size. Now drop that half-meter hunter into an ocean where the local apex predators are Leviathan-class monsters that run 50 to over 100 meters from head to tail. Being the deadliest hunter of the Cambrian does not make it the deadliest hunter of an alien sea. Those are two completely different exams, separated by 500 million years of evolution and a difference in scale so large it barely fits on the screen. Today, the animal gets graded on that second exam. The results are not what the reputation suggests, because reputation is exactly the trap. The phrase apex predator conjures size, power, dominance. None of those assumptions survive a leap across 500 million years in an entire alien biosphere. An apex predator is only ever apex relative to its own neighborhood. Change the neighborhood and the crown means nothing. That is the real experiment. Anomalocaris canadensis deserves a proper introduction. Most people know the myth, not the animal. It was a radiodont, part of an extinct group of stem arthropods and one of the largest animals in its world. It swam in shallow seas that later became the Burgess Shale in what is now British Columbia about 508 million years ago. The name itself is a fossil of a mistake. When pieces were first discovered, the front appendage was described as the body of a shrimp, the circular mouth catalogued separately as a jellyfish. It took decades before scientists realized these were parts of one giant predator, so the name literally means abnormal shrimp, a leftover from that confusion. The real body plan is more like this. A pair of segmented grasping appendages hang off the front of the head, lined with rows of curved, forward-facing spines, the tools it used to snatch and hold prey. Beneath those sits a strange circular mouth, an oral cone built from overlapping plates arranged like a camera aperture. Down each side of the flexible body runs a series of soft swimming flaps, and the animal moved by rippling them in a traveling wave, like a living sheet of muscle folding through the water. On its back sat rows of delicate gill blades for breathing, and crowning it all, a pair of enormous, stalked compound eyes. This was the master of its domain. It's worth stressing just how new that role was in Earth's history. The Cambrian was the moment complex animal life exploded into a staggering variety of body plans, and Anomalocaris was one of the very first animals big enough and equipped enough to actively hunt other sizable animals. It helped kick off the first real predator-prey arms race, the evolutionary pressure that pushed early animals to grow shells, spines, and armor in the first place. But it was still a domain of slow, soft, small prey in warm, shallow water, an ocean with no giants at all. And that context is going to decide every single score that follows. This is Survival Decoded, the series where I test fictional and prehistoric creatures against the harshest worlds in gaming and nature. And I want to be clear about what this is not. This is not fan fiction, and it is not me picking a winner because one animal looks cooler than the other. Every point I hand out today comes from real measurements, real anatomy, and the cold logic of selection pressure, the same forces that built this animal in the first place, and the same forces that would tear it apart in a world it never evolved for. If Anomalocaris earns a good score, it will be because the biology genuinely supports it, and if it fails, I will show you exactly where the numbers break, because on this channel honesty beats hype every time. I would rather give you an uncomfortable 4 out of 10 I can defend than a crowd-pleasing 9 I cannot. To answer whether this Cambrian hunter could survive, the evaluation breaks down into 4 categories, each scored out of 10. First, habitat adaptability. Can its body physically handle the range of environments in Subnautica? 2. From sunlit reefs to the deepest trenches. Second, dietary compatibility. Can it find, catch, and digest enough food in this ocean to stay alive? Third, competition and predation. Can it avoid becoming a meal in a sea packed with things far larger than itself? Fourth, reproductive success. Can it establish a breeding population that persists across generations rather than dying out in a single unlucky season? Adding those 4 scores gives a final survival verdict. After the numbers, the script turns to 3 ways this animal might evolve over deep time to better survive in an alien ocean. The question hanging over all of it is simple. Does a half-billion-year-old apex predator have enough left in the tank to clear the survival threshold, or does the deep simply swallow it whole? A note on scoring before the categories begin. A 5 out of 10 is not a passing grade. It is a coin flip, an animal that might scrape by under ideal conditions and die under bad ones. Anything below 5 means the environment works against the animal faster than it can adapt. Each number tells a story, survivor, or statistic. The categories start one at a time. Start with habitat, because before an animal can hunt or breed, it has to physically handle the water it's in. Anomalocaris evolved for a very particular kind of ocean. The Cambrian seas it thrived in were warm, shallow, brightly lit, and, this matters, lower in dissolved oxygen than anything you'd find today. Atmospheric oxygen was still climbing toward modern levels, so the water was thinner. In the sunlit shallows of Subnautica 2, a zone like the safe shallows from the first game, that evolutionary history works in its favor. Those giant stalked eyes were among the most advanced visual organs of their time. Fossilized radiodont eyes from Australia's Emu Bay Shale preserve roughly 16,000 lenses each. That count puts their visual acuity in the same league as a modern dragonfly, one of the sharpest-eyed hunters alive right now. In clear, sunlit water, that is a genuine advantage. It can spot motion, track a target, and line up a strike from real distance while staying unseen. And the warm upper reef is the one place where its undulating, flap-based swimming works the way it's supposed to, letting it glide and corner through open, gently structured terrain instead of fighting it. There's another quiet edge buried in its history. Cambrian seas held less dissolved oxygen than today's oceans, so this animal's metabolism was built to run on a leaner supply than most modern predators need. In a warm, biologically busy shallow biome, that lower oxygen demand is a margin of safety, one less way for the environment to kill it. In the top 50 meters or so, Anomalocaris is home. It reads the light, it reads motion, and it hunts the way it has for 500 million years. But Subnautica is not a game about the shallows. It is a game about going down, deeper and deeper into darkness and pressure, and this is where our contender falls apart. Anomalocaris had no mineralized skeleton and no protective shell. Its entire body was soft tissue, held together by muscle in a thin, flexible cuticle, no more armored than the skin of a modern squid. That design has a hard physical ceiling. Water pressure increases by roughly 1 atmosphere for every 10 meters of depth, so at 300 meters an animal is already carrying 30 times the surface load, and Subnautica's deeper biomes plunge far past that. Push a soft, unreinforced body into those crushing pressure zones, and there is simply nothing in the anatomy to resist the squeeze. No rigid frame, no pressure equalizing system. It is not making it into the abyss intact. And even if it somehow could, its single best weapon turns useless. 16,000 lenses are still just optics, and optics need photons. In the total darkness below the sunlight zone, high-resolution vision is worth nothing at all. The real predators that own those depths, in nature and in Subnautica alike, navigate with pressure sensing, electroreception, vibration, and touch, not sight, and Anomalocaris has none of those systems. Compare it to the soft-bodied animals that actually thrive in the modern deep sea, like certain squid and jellyfish. They survive down there not because they're tough, but because their tissues are watery and nearly incompressible, with no large gas spaces to collapse, and their whole physiology is tuned to the cold and the pressure from birth. Anomalocaris has none of that specialized deep-sea tuning. It's a warm, shallows animal, full stop, and dropping it into a trench is like taking a reef fish and firing it into the abyss. So the habitat picture is split cleanly down the middle, brilliant in the sunlit shallows and effectively helpless everywhere below them. That leaves it elite in one thin surface band and locked out of most of the planet, scoring Anomalocaris a habitat adaptability rating of 5 out of 10. Food first, because a predator that can't eat is already a dead predator walking. For decades, the popular image of Anomalocaris was a shell-crushing terror that cracked open trilobites like walnuts, and that claim still circulates. That image is almost certainly wrong. A 2023 biomechanical study reconstructed the animal's front appendages and modeled the forces they could handle. The appendages were far too slender and flexible to crush hardened mineral armor. Trying to bite through a trilobite's calcified shell would more likely have snapped the predator's own spines than the prey. Damaged trilobite fossils once blamed on Anomalocaris are now thought to come from other causes entirely. What this animal was actually built for is soft-bodied hunting. Worms, small, thin-shelled arthropods, larvae, and other squishy invertebrates, prey soft enough for those spined graspers to seize and pass back to a mouth that grips and tears rather than grinds. Some researchers even suggest it may have hunted up in the water column rather than on the seabed, using those big eyes to pick off small swimming prey silhouetted against the light above, and ambush from below style closer to a modern pelagic hunter than a bottom scavenger. That detail matters because it means its ideal hunting ground is open, well-lit, mid-water, precisely the kind of habitat that becomes a death trap the moment a larger predator shares it. The oral cone was a ring of overlapping plates that could open and close like a shutter, better suited to gripping, puncturing, and pulling apart soft tissue than to delivering a hard, crushing bite. Paired with those spined front appendages that swept prey toward the mouth, the whole system was a soft prey processing line, not a nutcracker. Body size sets a hard cap on prey size, too. At 38 to 50 centimeters, Anomalocaris could only handle targets a fraction of its own length, small enough for the grasping spines to close around completely. Anything approaching its own body size was off the table. That wasn't a matter of aggression. The grasp and shuttle mechanism simply had no leverage against a struggling animal of comparable mass. So the real dietary question for Subnautica 2 is not whether Anomalocaris looks fearsome, it's whether an alien ocean contains enough small, soft, catchable prey to keep a hyperactive, constantly swimming, half-meter hunter fed and alive. And the honest answer is, probably not nearly enough. The Subnautica food web is dominated by animals that are wrong for this predator. Many are armored with plating and hard structural shells that its soft mouth parts physically cannot process. Exactly the prey the 2023 study says it never had the equipment to handle. Others are simply too large. A 40-centimeter hunter can't overpower prey that size, or even get its appendages around it. And some are biochemically alien. Their tissue chemistry might be something a Cambrian digestive system, tuned for Earth invertebrates, cannot break down, or that could be outright toxic. Strip those groups out and the menu of small, soft, edible targets gets very thin, very fast. That matters more than it sounds, because an active pursuit predator runs on a razor-thin energy budget. An animal that swims continuously by rippling its flaps and strikes often has to bring in more calories than it burns every single day, or it loses body condition and dies. If the compatible prey is scarce, scattered, and hard to find, that math quietly turns negative and stays there. It would slowly starve in a sea that looks, to our eyes, absolutely full of life. There's a compounding problem on top of scarcity. Even the soft prey it could theoretically catch might be evolutionarily naive in a way that doesn't help, or worse, it might be defended by chemistry no Earth predator has ever faced. An alien small animal could be laced with compounds that a Cambrian gut simply reads as poison. So the pool of prey that is small enough, soft enough, catchable enough, and safe enough to digest shrinks with every filter. Being surrounded by food it cannot eat is biologically identical to having no food at all, scoring Anomalocaris a dietary compatibility rating of 3 out of 10. Category 3, Competition and Predation, and here the numbers go from unflattering to brutal. Put the scale in plain terms, Anomalocaris measures about 4/10 of a meter, roughly the length of a human forearm. Leviathan-class predators patrolling a Subnautica ocean run from around 50 meters for something Reaper, sized up past 100 meters for the true giants. That is not a rivalry. That is a length gap of more than 100 to 1. Because mass scales with the cube of length, it translates into a weight disadvantage running into the hundreds of thousands of times. And the gap stays hopeless even against the mid-tier residents, not just the true giants. A predator in the 10 to 20 meter range, ordinary by Subnautica standards, still outmasses Anomalocaris by a factor in the thousands. There is no size class in this ocean where a 40-centimeter animal reads as anything other than prey. The Cambrian never produced competition on this scale, so nothing in its body plan anticipates it. What that means is stark. In the Cambrian, Anomalocaris was the ceiling of its world. Nothing hunted it because nothing else had evolved big enough to try. It never developed defenses against a larger predator because, for its entire evolutionary history, there wasn't one. Drop it into a Leviathan ocean, and that whole identity inverts instantly. It tumbles from the absolute top of the food chain to the very bottom. To a Leviathan, this apex predator is not a threat, not a rival, not even a meal worth turning for. The cube law is the cruelest number in this analysis. Double an animal's length, mass roughly octuples. A Leviathan, 100 times longer than Anomalocaris, isn't 100 times heavier, it's on the order of 1,000,000 times heavier. Anomalocaris isn't a small predator in this world. It's plankton with ambitions. It is a single incidental mouthful, inhaled without the giant even registering what was swallowed. When a larger predator appears, can Anomalocaris defend itself? A honest inventory of its toolkit makes the answer stark. No armor. No mineralized skeleton to blunt a bite. No venom. No spines long enough to matter against something 100 times its length. No burst speed, flap-based undulation is efficient, not fast, so outrunning a Leviathan across open water is not an option. Strip away the list and Anomalocaris has exactly one survival mechanism left: avoidance. Its only move is to stay small, stay hidden, tucked into the structural clutter of shallow reefs, and simply never be detected. But even that last resort leans on the wrong sense. Those magnificent compound eyes only warn it of danger it can see coming, in bright water, from a direction it happens to be facing. A Leviathan hunting through the gloom with pressure sensing and sonar-like detection picks up the little predator's movements long before Anomalocaris has any idea it is being watched. It gets ambushed from below or behind, from a direction its vision for a sensory world was never built to guard. And there is a deeper problem beneath all this. Anomalocaris never evolved anti-predator behavior at all, because for its whole existence it had no predators to evolve against. It has no instinct to freeze. No startle response tuned to a looming giant. No ingrained fear of open water. None of the hard-won behavioral defenses that modern prey animals inherit from 100 million years of being hunted. It would swim through a Leviathan ocean with the confidence of a king, and that confidence would get it killed. There is no counterplay here, only the shrinking odds of not being noticed, and in a predator-dense alien ocean, those odds are grim and getting grimmer, scoring Anomalocaris a competition and predation rating of 2 out of 10. Reproductive success, the fourth and final category, is the one area where Anomalocaris can actually make a real argument. Like most early arthropods, radiodonts almost certainly followed what ecologists call an R strategy: release enormous numbers of tiny eggs into the water column and invest nothing in parental care afterward. When the death rate is catastrophic, that's exactly the right play. If nearly every adult ends up as Leviathan food, an animal doesn't win the long game by carefully guarding 2 or 3 offspring. It wins by flooding the system, spawning thousands of eggs at a time, and betting on sheer volume so that a tiny fraction survive the gauntlet long enough to reach adulthood and spawn again. That's how modern animals persist under heavy predation, from insects to many fish. In theory, a prolific broadcast spawner can absorb losses that would wipe out an animal that breeds slowly and produces few young in just a few generations. The scale of that output can be staggering. Modern broadcast spawners with similar strategies release tens of thousands to millions of eggs in the season, swamping predators with sheer numbers. If Anomalocaris followed the same pattern, a single spawning female could seed the water with more offspring than every Leviathan in the region could consume, at least in principle. It's genuinely the one strong card in an otherwise weak hand. But theory runs straight into an alien wall. Flooding the water with eggs only works if those eggs and the larvae that hatch from them can actually survive and develop, and here every single environmental variable is unknown and probably hostile. The water chemistry is foreign. The temperature regime is foreign. A Subnautica ocean is infamous for its microbial threats. The pervasive, waterborne bacterial menace drove the entire plot of the original game through the Kara pathogen. A biological threat like that could sweep through a batch of soft, defenseless Cambrian eggs before a single one ever reaches the larval stage. On top of that, there's no evidence that Anomalocaris or its young could tolerate the swings in salinity, pressure, and chemistry that dispersing larvae would inevitably hit as they drifted through an unfamiliar sea. Potential output is high, but realized survival of each new generation is very low. Enormous spawn, tiny yield, a factory running at full capacity with almost nothing coming off the end of the line. And there's a threshold problem lurking here. A broadcast spawning strategy only sustains a population if enough larvae survive to replace the adults that die each generation. Fall below that replacement rate for even a few seasons, and the whole population spirals toward local extinction no matter how many eggs get released. Given the pressure, the predation, and the alien pathogens working against every clutch, staying above that line would be a knife's-edge gamble, scoring Anomalocaris a reproductive success rating of 4 out of 10. So let's add it all up. Habitat adaptability earns a rating of 5 out of 10, dietary compatibility a rating of 3 out of 10, competition and predation a rating of 2 out of 10, reproductive success a rating of 4 out of 10. That is a combined total of 14 out of 40, which rounds to an overall survival score of 3.5 out of 10. And here is the verdict, delivered straight, the way this channel always does it. Anomalocaris does not survive Subnautica 2 as a global animal. It simply cannot. The pressure crushes it out of the deep, the 100-to-1 scale gap feeds it to the Leviathans, and the armored, oversized, biochemically alien menu starves it in open water. But notice that it does not score a 0 either, and that nuance is the whole point. In the warm, sunlit, structurally sheltered shallows, this predator is genuinely competent, its ancient 16,000 lens eyes and its undulating body still doing exactly what 500 million years of evolution built them to do. So it survives, but only by radically shrinking its ambitions. The apex predator of the entire Cambrian ocean gets demoted to a coastal, shallow water specialist, clinging to the one thin band of the map where its ancient toolkit still pays off, from king of the Cambrian to back reef survivor. That is a genuinely humbling 500 million year takedown. And honestly, that outcome tells us something bigger than one animal scorecard. Dominance in nature is never a permanent trophy an animal carries with it. It is a lease granted by a specific environment, and it expires the moment the environment changes. Anomalocaris didn't get weaker over 500 million years. The world just stopped being the one it was built to rule. And that's the quiet lesson that runs under every episode of this series. When we ask whether a creature from one world could survive in another, we're really asking how much of its success was the animal itself and how much was the stage it happened to stand on. For Anomalocaris, the honest answer is that an enormous share of its legend was the stage. And make sure you stick around until the end, because after that we will explore 3 ways this animal might evolve over deep time to better survive in an alien ocean. A single generation gets crushed. Evolution does not work on single generations, though. It works across deep time. Given enough of it, selection pressure could reshape this animal into something that truly belongs in an alien ocean. 3 possibilities stand out. The first branch is the shallow water specialist. Selection leans harder into everything that already works. The compound eyes sharpen further, the swimming flaps grow more efficient, the whole lineage commits fully to the sunlit reefs. Camouflage improves, reflexes quicken, motion detection gets finer, all to dodge anything that wanders up from the dark below. It never conquers the planet, but it becomes a nearly untouchable master of the surface zone, thriving in the exact niche where it already scored highest. It is the evolutionary version of doubling down on a best category instead of trying to fix the worst ones. This is the safest of the 3 paths, and probably the most likely, because it asks the least of the animal's fundamental body plan. The second branch is the pressure adapter. Populations push steadily deeper face, relentless selection for a body that can take the load. Individuals with a thicker, partially reinforced cuticle fare better. Over enough generations, sensory organs shift from light to pressure and vibration, letting the lineage finally hunt in the darkness where the original animal's eyes were dead weight. This is the hardest road of the 3, because it asks evolution to rebuild the animal's most basic limits, its pressure tolerance and its entire sensory world. But the deep sea is also the largest habitat on any ocean world, so the reward for cracking it would be enormous. The third branch, the hyperpredator. Selection keeps favoring larger bodies with tougher, more heavily reinforced front appendages, generation after generation, until the lineage finally cracks the armored, mid-sized prey the originating animal could never touch. It's closing a gap on a menu that was once out of reach, one small step at a time. A true Leviathan remains out of the question. The cube law forbids it on any plausible timescale. But the animal climbs from incidental snack to respectable mid-tier predator, big enough that the giants don't swallow it without a thought. That alone rewrites its survival odds. Evolution isn't choosing any of this on purpose. There's no plan, no goal. In each environment, the bodies that happen to fit survive and reproduce. Over millions of years, those tiny statistical edges compound into a genuinely new animal. So which of the 3 would you bet on? The shallow master, the deep adapter, or the giant? Let me know in the comments what creature you want me to analyze next. If you liked this, hitting like and subscribe keeps you in the loop for future videos. And if you'd like to support the channel further, YouTube members get sneak peeks, early access to new releases, and custom emojis of their favorite creatures from the channel. Until next time, stay curious, and I'll see you in the next video.